Several questions.
Sure.
So, discrepancy between computed and experimental spectra, would you interpret as the shortcoming of the methodology, or there was a different morphologies of porphyrins on experiment and porphyrins that you were computing, or both?
Well, I know for example, the exact same porphyrin, the iron octaethyl porphyrin, with a tyrosine on it, or with a phenol on it, and carbonyl bound, looks basically exactly like the spectrum I showed.
Okay.
It's slightly shifted. It's a little bit red shifted. Usually iron's a little bit bigger, or a little different than the nickel, so it causes the ring electronics to change a little bit because it's smaller. It shrinks it a little bit. But overall, it should. It will. Basically, all of them have one really big band, one that's about 10% that size, and one here that's 5% of this one.
Okay. So, what is the approximate relative error in the transition energy and relative energy in relative error in intensity? Just what is mostly suspicious or what is mostly positive?
Well, I mean, I looked out past this, and it didn't seem to have, this. If these were the same, there didn't seem to be any of this going on out here.
So relative intensities of Q band and S band.
Yes.
Is your major suspicion?
Well, Q and B. This is the B band.
Okay, Q and B.
Yes. Yes.
But Q band itself is not terribly bad.
No, I mean, if you were calling these two Q bands, I mean, they're in approximately the right position. You just expect something, if this is at roughly 7 or so, you would expect something about 70 at 400 here.
Okay.
So to answer your question, I don't know exactly why it went wrong.
Which functional you were using, and do you believe that trying different functional may improve the results?
I don't remember what functional we used. PBE?
Yes, correct. Good answer. Okay.
But yeah, so different functionals may be helpful for this.
So in your middle figure here, the Q band changes upon modification of the ligand.
Yes.
How would you interpret it from the analysis of ligand strength? Does it matches your intuitive expectations?
Well, I mean, if we disregard the tyrosine one, because obviously that one fell off, right? It wasn't a ligand anymore. If you go from 500 to basically 600 by having the anionic phenol, I guess that would make at least some sense. But there isn't a whole lot out there drawing parallels between necessarily why one Q band is where it's at.
Mm-hmm.
So experimentally wise, they basically just say it is here at 552. They don't say necessarily, at least I haven't come across a paper where they've correlated 552 means that there's, in this case, no ligands, and then 559, that means that there's a histidine there. It doesn't seem to have that sort of correlation. So I'm not sure exactly why it would be shifting.
Good. Do you expect very impressive precision from DFT? Does DFT has promise for excited states, or it is a theory only for ground state?
I mean, DFT can calculate excited states. And I mean, it works for excited states. We did do some of those. But I don't know.
Under which approximations?
I think we did it at 0K. And
any other approximations?
Independent orbitals.
Okay, good, good. Would you agree that there are some additional methods that are more appropriate? So what are the names for methods for excited states?
With time-dependent DFT works.
Okay, okay, yeah. Very good, very good. So you are showing only HOMO orbital.
Yeah.
And some of them were localized on iron,
yeah.
Some of them were localized elsewhere. If you would screen all available orbitals,
okay,
how many of those would have D character and localize on iron?
There should only be 5.
Yes.
There should be only 5 orbitals that have D character.
Very good.
Granted, they're linear combinations of all atomic orbitals, but they have mostly D character.
Okay. Okay. And are they all expected to be occupied, or all of them are expected to be unoccupied, or it is proportion?
Well, it depends on the oxidation state and if it's high spin or low spin. So, in this case, iron 0, it has 60 electrons. So it should be, and since I stipulated that using a carbonyl, it should be in a low spin state. It's a very strong filled ligand. So there should be 3 filled orbitals here with 2 unfilled D orbitals. And then when you go to iron 1, it will be 2 that are filled, 1 that has 1 electron in it, so it's a doublet, and then 2 that are unfilled. And then the ferrous iron here, iron 2, should be 2. No, wait. Iron is D8, sorry. 4 filled, 1 empty. 3 filled, 1 half, 1 empty. 3 filled, 2 empty. And then 2 filled, 1 with 1 in it, 2 empty. Does that make sense?
Yep.
Okay. Yeah, so iron 0 has 8 electrons. Or D electrons.
Very good. So, your personal impression, what was useful in this course, and which of these methods and approaches would be applicable to your major research?
I mean, just learning how to use the software and building models and that sort of thing is very useful. I will answer your question slightly differently, from a different angle. I would have liked to got into some vibrational spectroscopy, because that's what we do in our labs, look at vibrations. And so, and I know that DFT can calculate them. I don't know how intensive it is, but I know that people have ran Raman DFT calculations. And I think that would have shown us some more information on these systems.
Okay. I would like to thank you for nice answering on the question session, and congratulations, you are getting A in this course.